has improved upon some of the memory allocation techniques which C uses. The improvement is in the usage and also to accommodate some of the powerful features of C++, such as classes, its constructors, and destructors. So let's take a quick flashback into how memory allocation in C works, because we'll build upon that and talk about differences between C and C++ when we go into memory allocation in C++. A trip down memory lane to talk about dynamic memory allocation in C. There are two common keywords that we used, one to allocate memory and one to free memory. Malloc is a special function which was provided by the stdlib.h library in C to allow developers to manage memory, allocate memory for their use. As a developer, if you allocated memory, you were responsible for freeing memory as well. And the keyword or the function that you used to free memory was the free, and you passed in the address of the memory that you wanted to free. A quick overview of how the malloc function works. The malloc function returns a void star. A void star basically means that it can point to anything. So that's the return value of the malloc, and it takes as an input a number which specifies the size in bytes of the memory that we want to allocate. So a void star pointer indicates that the pointer can be to any data type. And depending on the kind of data type we were instantiating, we simply cast the void star to the correct pointer type that we were looking for or that we were allocating memory for. The int num specifies the size in bytes of how much memory we want to allocate. Is it the size 4, which is typically the size of an integer, or is it of size 1, which is the size of a character pointer, and so on. Here is a quick example of how we used malloc to allocate memory for an integer. So int pointer is a pointer to an integer. Note that we cast the return type to int star and we malloc the size of int. Size of was a helper method or a helper primitive which allows us to figure out what the size of primitives, structs, and constants are so that we can allocate memory for them. Size of is typically used with malloc to figure out how much space we want to allocate. In C, and this will be true in C++ as well, whatever memory you as a developer allocate, it's your responsibility to free it as well. The function that you use to free memory is the free function, which takes in a void star address. Void star address means you can pass in the address of any data type and it will free up the portion of memory used by that data type. So note that free returns nothing. It's a function which returns void, and it takes in a void star address, which means it can take in a pointer to any data type. There's an important thing to remember about freeing memory. Memory for variables that's allocated by the CPU is not to be freed by the developer. So let's take an example of memory that you allocate, which is int underscore pointer, and you call free on it. That's completely correct, and it frees the memory space that int pointer used. However, the integer a is not a pointer and memory for it has not been allocated by you. It's allocated by the CPU itself when the C program is run, which means you can't call free a. That's an error. Let's also do a quick overview of the different types of memory available to a C program. Stack memory versus heap memory. There are two types of memory that's available when we run a C program. This is the memory that is used to store variables and any other structs or other data that we set up in the C program. The first is the stack memory. This is entirely managed by the CPU. It's responsible for allocating space in the stack memory and freeing up space as well. Developers do not allocate or deallocate space on the stack. So anytime you define a primitive variable such as integer, char, etc. in C, memory for it is allocated in the stack memory portion. When you call malloc, or any of the other memory allocating functions in C, the space that you use to allocate this memory for your pointer variable is the heap memory. This portion of memory is managed by the developer writing code in C. The developer allocates memory. It's the developer is also responsible for freeing up the memory in the heap. The stack memory is one that's managed by the CPU. We saw that. The memory allocated when you simply declare a variable and then immediately use it, like int a, char c, float f, or maybe you have a struct point3d and you declare a variable of that type. The memory that you declare in this way and that you use in this way, the variables that you use in this way, all live on the stack. They are put on the stack by the CPU, and the CPU takes care of removing it from the stack as well. The reason it's called stack memory is because it behaves like a stack. As you declare variables, the memory for those variables are pushed onto this stack-like structure, and newer variables are put on top. As we exit functions, variables cease to exist and they are popped from the stack. Stack variables only exist so long as the function which created those variables is being executed. The minute you exit from that function, the stack variables are popped from the stack memory and they cease to exist. When you use malloc to instantiate memory for a pointer, whatever the kind of pointer it is, it goes in the heap region of your computer's memory. This region is not managed automatically and is used for memory for pointers. The developer is responsible for managing memory in this region. He can use functions like malloc and free to do so. If a developer forgets to free a piece of memory that she has used earlier, then that can result in a memory leak. Memory leaks basically can cause your program to run out of memory. Here are some brief highlights of the differences between stack memory and heap memory and how they function. Accessing a variable which is placed on the stack is extremely fast. Access to pointers and the data associated with pointers tend to be a little bit slower. Since the space on a stack is managed by the CPU, it's extremely efficient. It's managed automatically. It does not get fragmented. Space on a heap is managed by the developer, and because we allocate different sizes of variables on it, and it's not really a contiguously located memory, it can get fragmented. Variables whose memory sits on the stack are in the scope of the function declared. So you typically declare local variables within a function, and they are applicable and can be used only within that function. Once you move outside the function, you can no longer access those variables. Variables which are declared on the heap using dynamic memory allocations are global in that across functions, you can access the data in those variables. The CPU and the C program together has to partition the memory into stack memory, those which is used for stack, and those that will be used for heap. The stack memory typically tends to be smaller in size. There is a clear size limit. So you can't put an infinite number of variables in the stack memory. Heap memory tends to be much larger. It's only limited by the amount of memory that's present on your computer. Malloc is not the only function that allows you to allocate memory. There are other functions which help you do things a little bit more easily. And one such is the calloc or the calloc. This is a special function which is useful to allocate memory for arrays. The thing about arrays is that you have to allocate memory for the array itself based on the size of the data structure of that array. Calloc allows you to do this easily, where it allocates memory for num elements, that's the number of elements specified, where size is the size in bytes of each element. So instead of doing something like what you see on screen, in this example, we use malloc, and basically get the total size of the array that we want to allocate, which is 100 multiplied by the size of integer. That's an array to hold 100 integers. Instead of that, we could have simply used calc and specified that we want 100 elements and each element is the size of an integer. It's just a cleaner way of memory allocation for an array. C also lets you change your mind about how long an array is going to be and allows you to make it even longer, that is, increase the number of elements. If you originally allocated space for 100 elements where each of those elements were an integer, this is how you did it. Say you did it using malloc, and now you realize that instead of 100 integers, you want to store 200 integers. You could use realloc to increase the size of that array, as you can see on screen. Realloc takes in the original address, note the ARR passed into realloc, and then increases the size of the array starting at the same address as earlier. An important thing to remember about realloc is that it starts at the same address as the one originally allocated. There's no change in the starting address. The whole idea behind realloc is that the original elements that you placed in the array will be preserved. It simply tries to increase the length of the array in the contiguous block immediately after the original array ends. So it tries to extend the memory allocated to that array. If it doesn't manage to extend it, realloc will fail. Realloc helps in that you don't have to copy the original elements over to the new array. It's also not that great in the sense that if you don't have a contiguous block of memory starting at the original address to accommodate the 200 element array, realloc will fail. It's always possible that when you try to allocate memory for a variable, an array, an integer, or whatever that variable is, using malloc, calloc, or realloc, that there is just not enough memory available to accommodate your request. In such a case, all of these functions will return a null pointer to you. So it's important in C, whenever you allocate memory, to check that the return value is not null before you go ahead and use that pointer. This was a very brief flashback into how memory allocation in C works. It's important that you have the fundamentals of this right because C++ builds on top of this. We'll be talking about the differences between C and C++ in memory allocation, and it's important that you completely understand what malloc, realloc, and calloc does and how free works in C. On to C++. Memory allocation in C++ has to consider a very important aspect of C++, which is not present in C, and that is classes, objects of those classes, which are instances of those classes, and the fact that classes have constructors which initialize and set up an object to be in the correct state, and destructors which basically clean up after the object. So when we allocate memory for a class, we need to make sure that constructors and destructors are also accounted for. Let's look at a very brief flashback of what classes are. We'll be using all of this in new and delete. So if you're very familiar and comfortable with classes and objects, you can skip this portion. However, this is just a recap to kind of solidify your foundation. So what are classes? They are structs which contain functions if you come from C. Classes basically exist because often you have a group of variables which form a logical unit and belong together. All information about a person, for example, forms a logical unit and may belong in a person class. Some of the information in a person class is of interest to the outside world. So any code which uses this person class might find some information about a person interesting, which means that information should be marked public. Stuff which is marked public is accessible to calling code or the outside world. What you consider internal plumbing of a class Things which are used to calculate information inside a class but not interesting to the outside world should be considered private and should be marked private in a class. A class allows this facility to mark stuff public or private. This group of information about a logical unit becomes a new user defined type. A class is a way for you as a developer to define a data type which is on par with integers, floats, doubles, or any of the other primitives that you see in C++. So once you set up a new data type by defining a class, anyone can create a variable of the class type. When someone creates a variable, they are set to instantiate the class, create an instance of the class, or create an object of that class. When you create an object, it's not just about allocating memory for all the stuff that has to be stored inside the class. It's also about initializing the class to have the right values for each of the data variables present inside it. And once initialized, when you no longer use that object, you'd want to clean up those data variables. This is where the differences in memory allocation come in between C and C++. And lastly, what makes classes cool is that anyone can use a pre-existing class and build on top of it, build more complicated classes, structures, or logical units on top of this class. These ideas put together form the foundation of object-oriented programming. Now, we'll see how we use dynamic memory allocation with classes, constructors, and destructors. We'll see how the C++ dynamic memory allocation works with these constructs. Hopefully, at this point in time, you've conceptually understood how C's dynamic memory allocation works. Now, the dynamic memory allocation in C++ is very different from how it is in C. Conceptually, they're the same, but all the things that C++ has to do to instantiate classes, etc., is much more advanced and demands much more from the functions which allocate and deallocate memory, which is why dynamic memory allocation has completely new functions or keywords in C++. So it's nothing that you've seen before. Keep the C concepts in mind, and we learn 5 rules right now in order to completely understand and use the dynamic memory allocation keywords in C++ correctly. The first most important rule is that when you use dynamic memory allocation in C++, never use the malloc and free functions. Malloc and free is available in C++, but if you want C++ constructs like classes and everything else in C++ to work correctly, never ever use malloc and free. Just because it compiles does not mean it'll actually work. So discard malloc and free, ignore them. You're never going to use it in C++. That was rule number 1. Rule number 2 says that you use the keywords new and delete for single variables of all types. Whenever you want to allocate memory for a variable, whether it's a pointer to a simple data type or it's a pointer to a class, use new and delete. New is the keyword to allocate memory, and delete is the keyword to free up memory. Use just new and delete in C++ in every place where you want to allocate and deallocate memory. That was rule number 2. Moving on to rule number 3. The new and delete keywords have different variations. There is a variation which we use with arrays, which we'll call new square brackets and delete square brackets. Anytime you want to instantiate an array, whatever the data type, whether it's a primitive, integer, float, double, or it's an array of classes, use the new with square brackets. Whenever you want to deallocate memory for an array data type, whatever the array is, use delete with square brackets. This is extremely important because the way arrays get allocated memory and the way single data types, a single integer, a single complex number class, etc., get allocated memory is completely different. So use new with square brackets and delete with square brackets when dealing with arrays. That was rule number 3. Moving on to the next rule. Here is a corollary of rules 2 and 3. Do not mix new slash delete and new in square brackets slash delete square brackets. Meaning, if you've used new without square brackets, the delete function that you have to use to deallocate that bit of memory is the delete without square brackets. Similarly, if you've allocated memory for an array using new with the square brackets, the way to deallocate that same bit of memory is to use delete with the square brackets. Do not mix and match these, because even though the keywords are the same, their behavior when used with and without square brackets is completely different. That was rule number 4. Do not mix and match news and deletes. On to rule number 5. Rule number 5 states that all pointer member variables in a class that you define and declare should be cleared up in the destructor that you write. So if you imagine a class, it has a whole bunch of member variables. Some of these member variables will be pointers. That's just the way it is. You may not have any pointers, but if you do, then you need to deallocate memory for these pointers in the destructor of your class. This basically ensures that anytime you have a class, it cleans up after itself. Outside the class, typically no one knows what member variables you have and what pointers you have allocated. It's only inside the class that this information is available. In that case, it means that you have to clean it up yourself in your class in the destructor. These are the 5 rules to remember when you allocate and deallocate memory in C++. This is extremely important because these lay the framework for using memory allocation and deallocation correctly and avoiding unpleasant, unnecessary errors which then become very hard to track down. Follow these rules diligently and you'll minimize your errors. We saw the 5 rules which a developer has to follow in order to be able to use new and delete correctly. Or rather, the 5 rules which a developer has to follow in order to do dynamic memory allocation in C++ correctly. Following these rules ensure that you are not left with tricky bugs that is hard to debug. You minimize the chances of tricky errors. Now, there were a lot of rules and we just threw them out there. Let's take them one at a time and see what each of those means. We'll also see examples of what happens when we violate these conditions, the kind of issues that we run into. We'll start with rule number 1. Malloc and free work perfectly well in C. However, never ever use them in C++ ever. And why is that? This is because the nature of memory allocation in C++. Malloc and free only assign memory. They only assign space to store either an integer, float, or any struct that you've defined. C++ requires more than that. C++ has classes. And even their primitive type, all of them have constructors. Malloc and free do not know about constructors because they are a C construct. Malloc and free do not call constructors nor do they call destructors, which means the space to hold your variable might be assigned, but setting up your variables correctly, setting up all the member variables of a class correctly cannot be done when you use malloc. And similarly, when you clean up after yourself, if you clean up a class, if you do not call the destructor, you don't clean up the class correctly. Malloc and free only assign memory. They do not call constructors and destructors. The importance of this rule cannot be emphasized enough. Using malloc and free in C++ has terrible consequences. Very strange consequences which you don't realize. Because in C++, you naturally expect constructors and destructors to be called, and malloc and free simply violates this glibly. Do not use malloc and free and avoid terrible, terrible consequences. That leads us right into rule number 2. Instead of malloc and free, we use new and delete for single variables of all types. And by single variables, we mean variables which are not arrays. So it doesn't matter whether the single variable is an integer or a class. Anytime you need to create a single variable of a pointer type, just use new. And new allocates and constructs the variable. What does this mean? This is important. New will allocate memory to hold that variable. It will also call the constructor for the variable. So new does two things. Remember, malloc only does the first, allocate memory. So basically, if you're setting up a new for a class, say the complex number class which has two floats within it, it'll set up enough space for the two floats. In addition, it will also call the constructor of the complex number class, so that the class is initialized correctly in addition to having the memory that it requires. New can be used with simple types such as integers, floats, doubles, characters. It can also be used with objects, that is classes. So new can also be used to instantiate objects of classes. Now the one thing about classes is that their constructor often takes in arguments. If you use the keyword new, you can also specify arguments which you want to pass into the constructor of that object or class. So new is flexible that way. You can call the default no argument constructor, or you can call any of the constructors which require arguments. Once you've allocated memory and constructed the object using new, you need to now free up and deallocate the memory of this object at some point in time. So anything that you allocate plus construct using new, you clean up by using delete. That is the perfect corollary. So do not use new and free. For example, if you've used new, you use delete to clean up after yourself. So what do these do? New, the order in which it performs stuff, will first allocate memory and then call the constructor for your variable. The constructor can be however complicated. It may or may not take in input arguments, but new will take care of all of that. It will first assign space where the variable data will live, and then it will call the constructor for your variable. In order to clean up memory which you've allocated and constructed using new, delete will first call the destructor and then deallocate memory. So what delete will do is call the destructor, which will basically ensure that everything inside that class or object cleans itself up, and then remove memory that's been assigned for that variable. So that's the order in which these operations occur. This order is important. It has to be done in this way so that you kind of have an orderly way of allocating memory, constructing an object, then destructing an object, and then deallocating memory. It makes logical sense. So we just said that delete will first destruct the object, that is call the destructor on an object, and then deallocate memory. It goes without saying, but it's still important that I mention it so that it's not lost, that we never use the variable after the call to delete. So if you've deleted a variable, whether it's an integer, a float, or it's a object of type complex number, once you've called delete on it, you never use that variable again, because it basically means everything inside the variable has been destroyed. The object itself has been destroyed and nothing sane exists within it then. On to rule number 3. So far we've spoken about new and delete. Rule number 3 speaks about new with square brackets and delete with square brackets. This is used exclusively for array variables, no matter what the type of the array. The array can be a simple data type like integers, floats, doubles, and chars, or it can be a data type which is user defined, that is, classes. Whether it's arrays of simple data types of arrays of classes, use new with square brackets and delete with square brackets to allocate and deallocate memory for it. New with square brackets not only allocates but also constructs the array. Remember that C++ is not just about memory allocation but also calling constructors on the individual array objects. So new with square brackets does both. It will allocate and construct the array. New with square brackets deals with arrays, which means that it will walk through every element of the array and call the no argument constructor for each element. This is why it's important to use new with square brackets. It realizes that this is an array that needs allocation and construction, sets up the memory correctly, and cycles through the entire array and calls the constructor for each of it, each element, the no argument constructor. One thing to note is you can't pass in arguments to the constructor when you use new with square brackets. That's kind of a limitation of new with square brackets, in that if your array is made up of elements which have constructors which need arguments for initialization, then you cannot use new with square brackets. It will only call the default no argument constructor. What you'll then have to do to initialize the variables to the values that you want is to call explicit setter methods on each object. So do remember that new, when used with square brackets for constructing arrays of objects, will call the default no argument constructor. Anything that you allocate and construct using the keyword new along with square brackets, you should clean up using the keyword delete again along with square brackets. These are perfect corollaries of each other. If you use new with square brackets, you use delete with square brackets. Let's dig a little deeper into what new with square brackets does. New will first allocate memory for the array. The array itself takes up memory. That's what is first allocated when you use new with square brackets. Then it will go to every element in the array for which the memory has been allocated and call the default constructor for each array element. It will also track the array length. So it knows how long the array is and it knows how many elements that it has to construct. That was the order of new with square brackets. Delete with square brackets will first call the destructor for every array element. Delete also knows how long the array is. It will cycle through every element, destruct the element by calling the destructor, and then deallocate the memory for the array. Once it knows that the destructor has been called on all the elements in the array, it knows it's safe to free up the memory which the array itself uses. Once again, I'll mention something that's obvious but absolutely needs to be said about the use of delete with square brackets. Anytime you call delete on a variable, delete with square brackets that is, never use that variable after that. That's because you've destroyed it. It's no longer in a state in which it can be used. You've called the destructor on all the array elements and you've deallocated memory for the array. Do not use that variable once you've called delete on it. Moving on to rule number 4. Rule number 4 combines rule number 2 and 3 together and specifies that you should not mix and match new delete with new with square brackets and delete with square brackets. So anything that you allocate and construct using new, you have to clean up using the delete keyword. And anything that you allocate and construct using new with square brackets, you clean up using delete with square brackets. So even though the keywords are the same, new and delete, the presence of the square brackets changes how they behave. So you do not mix and match these. We'll focus on what each of these keywords do and see a visualization of how they behave, and then you'll understand why not to mix them up. So allocation plus construction using new. So new will first allocate the memory space and then call the constructor for your variable, and delete will first destroy or call the destructor on your variable and then deallocate the memory space. Let's focus on allocating memory. New will first allocate memory. So if you imagine allocating memory as basically reserving a space, let's say that this ellipse on screen is the space reserved for your variable. So this is the space. It's a holding, like a compartment. It holds the information and that has been allocated to you. But we are not done yet. When we are working with objects, this allocation is not the end of what new does. After the space in memory has been reserved for your variable, new will then call the constructor for your variable. Within the constructor, you would have initialized many of the data member variables of that class. So let's assume that each of these circles that you see on screen is a data variable or a member variable of your class. Each of them get a valid initial value in the constructor. So new will call the constructor as well, so that not only do you have space for your object, each of the member variables within that object have the correct values when an object is initialized or set up. So new takes care of both of these. Now for delete. Delete will first call the destructor on the object created. So remember, this is how the object looks initially. It's got space to live in and each of its member variables have some values that's indicated by the solid circles. Delete will call the destructor, which will basically ensure that all the member variables are cleaned up correctly. If your member variables are pointers, then you yourself have to call the destructors of those member variables within the destructor of the object or the class that you've set up. So delete will first call the destructor, which means that your object once more looks like what you see on screen. Everything within the object has been destructed, only the memory space remains. Once the destructor has been called, the delete operator then simply deallocates the memory. Remember that this is the memory space that we are left with. We no longer need it because we've called delete on the object. Delete then deallocates the memory and it's free for anyone else to use. Now let's consider how new with square brackets and delete with square brackets behave. We've already seen that anything that you allocate and construct using new with square brackets specified, we have to clean up using the delete keyword with the square brackets. So what does new with square brackets do? It's used with arrays and it will first allocate memory for the array. Once memory for the array is allocated, it calls the default constructor for each array element. It knows and tracks the length of the array and calls the default constructor for each array element. Delete does the exact opposite. It will first call the destructor so that every element in the array has its destructor called, and then deallocate the memory for the array itself. So remember that new tracks the array length. Let's focus on the very first thing that new with square brackets does. It will first allocate memory for the array. Remember that the array is a list of elements. So the memory that will be allocated looks like a list of elements, and each element has its own constructor. So new has now only taken care of allocating memory for the array. Again, new with square brackets because that's what we're discussing here. Once the memory for the array has been allocated, new will call the default constructor for each array element. So we have every array element here. The default constructor will be called for each of them, and the member variables inside each element will get its correct default values. So see that it looks very different from the new without square brackets. The new with square brackets, the entire operation is very different from the new without square brackets that we saw earlier. Moving on to the delete keyword with square brackets. That first calls the destructor for each array element. We know that once the array element has been constructed, it looks kind of like this. Calling the destructor basically destroys each individual element in the array. So we are back to where we started, where only the memory is allocated for this particular array. Each element, because the destructor has been called on it, has been destroyed, is no longer a valid element. The delete with square brackets first makes sure that each element is invalidated by calling its destructor. And then finally, we have the very last step. The array memory is still allocated. Delete with square brackets will now deallocate the memory. The memory is now free for anyone to use. The visualization of how new and delete function, as opposed to how new with square brackets and delete with square brackets function, should have made it very clear that they are not fundamentally compatible operations. New is not compatible with delete with square brackets, and new with square brackets is not compatible with the simple delete. Don't mix and match them. Use the correct pair at any point in time. On to the very last rule. The last rule says that within an object or within a class, it's your responsibility to clean up all the member variables which are pointers, and you do this in the destructor. So clean up all pointer member variables in your destructor. That's the very last rule that you have to remember when you're working with dynamic memory allocation in C++. The entire purpose of having destructors within a class is to basically have a placeholder for where you clean up the class itself. Destructors are especially important when your class has pointers or file handles amongst its member variables. Pointers means you have to allocate memory. Once you allocate memory, it's your responsibility to free it up, and the place for you to do it is in the destructor of a class. Similarly, file handles, if you open it up, if you open and access a file, it's your responsibility to close the file. This is also something you can do in the destructor. The presence of the destructor gives you a placeholder for you to perform these operations. It's your responsibility to make sure that you clean up your class by deallocating memory for the pointers and closing file handles in the destructor. You do not clean up your class When it's destroyed, by not freeing memory or by not closing file handles, it can lead to serious bugs. It can lead to memory leaks, which can cause your program to run out of memory, and resource leaks, which means unpredictable things can happen when you use that file next. Clean up after yourself in the destructor of the class that you've created. This brings us to the end of the detailed explanation of how those 5 rules work in order to make your allocation and deallocation of memory in C++ work successfully. Now, let's see them in action using examples. We'll see what happens when we violate these rules in real life. We know the 5 rules which we need to follow in order to ensure that we work with dynamic memory allocation in C++ correctly. Let's look at examples which reinforce and show us why those rules are needed. The very first rule is we should never use malloc and free in C++ ever. So we are going to stop using malloc and free. But first we'll see an example of what happens if you use malloc instead of new in order to set up an object of your class. A quick refresher before that of why we don't use malloc and free. Malloc and free are constructs from C. C did not have the concept of classes and did not have the concept of constructors to set up a class in the correct initial state and destructors to clean up after a class. Malloc and free only assign memory. They do not call constructors and destructors. Using malloc and free, which basically is completely ignorant of the concept of constructors and destructors, has terrible consequences when we use them in C++. That's because you're expecting something to happen and that does not. Let's see this using an example. Let's make sure that malloc does not call a constructor. Take a look at this code on screen. We have a pointer to a complex number called C dynamic, basically indicating that this particular pointer requires memory to be allocated dynamically. What we've done here in this example is used malloc, a C construct, to create a dynamically allocated object. So how we've used malloc is the correct way to use malloc. However, malloc itself is the wrong function to use. Note that we specify the size of complex number to allocate the right amount of memory, and we cast the pointer returned by malloc to a complex number pointer. Now, when we run this code, you can be sure that no constructor is called. That's because if you go back and remember the complex number class that we set up, and if you remember its constructors, you'll know that you have a way of indicating when a constructor has been called on this class. Take a look at complex number and you'll notice something right here. Notice that complex number has 3 constructors, including a copy constructor. There is a print statement inside each of these constructors. It specifies what the constructor is: no argument, to argument, or the copy constructor. None of these print statements have been called. Notice the print statements there: no argument constructor, the to argument constructor, and the copy constructor. If you notice the output of running the code where you use malloc to allocate memory for the C dynamic variable, you'll see that none of these constructors have been called. There is no output message on screen, which means none of these constructors have been called. You take this piece of code and you run it using the malloc statement, the code which has the malloc statement. Nothing is printed on screen when we run our code. there is no message from the constructor. If any of the constructors had been called, we'd have a message from the constructor. Look at all the messages there. There's nothing about any constructor being called, which basically means none of the constructors were called. And the reason for that is we've used malloc instead of new. Malloc only assigns memory. It does not call any of the constructors. So what exactly happened? Memory was assigned, no constructor was called. We have garbage values inside our complex number variables. The real is 0, but the complex value is basically some garbage value. So in spite of having constructors which initialize these values to something sensible when the object is set up, we still have garbage values inside our member variables. If you don't use the constructor, having it is pointless. So never use malloc in C++. It bypasses constructors and destructors, and that completely defeats the purpose of having them in the first place. We have them because they are incredibly useful and help set up the object-oriented paradigm. Bypassing them leads to terrible consequences and subtle bugs which you'll find extremely hard to track down later. The next example that we'll look at here will show us how to actually use the new and delete keywords. So new and delete can be used to construct and allocate memory for single variables of all types, whether it's simple integers, floats, or any classes that you've set up. Anytime you need to create a single variable of a pointer type, we just use new to both allocate and construct that variable or that object. This can be used with simple types as well as with objects. The new keyword also allows you to pass in arguments to the constructor when you instantiate an object. So remember, new and delete are used together. New is used for single variable types, single data types, whatever the data type, whether it's user defined or built into C++. Take a look at the code on screen. Here we have a float pointer, and we basically allocate memory and construct this pointer variable by using new. So you can see highlighted on screen, float dynamic is the name of the variable. It's dynamically allocated pointer variable to a float data type is equal to new, that's the keyword that we use, float, and in brackets we pass in one argument, which is the value of the float. The float data type, which is built into C++, has a constructor which takes in one argument, which is what we are using over here. If you take a look at the output when you run this piece of code, you'll notice that the float indeed has the value 23.3. So you can see the output, dynamically assigned float has value 23.3. That's the cout statement which prints this to screen. After we've created the float, output it to screen, printed its value to screen, we then delete the float dynamic variable. Note that because we used new without square brackets, we use delete without square brackets in order to call the float's destructor and to deallocate the memory associated with it. Let's look at one more example where we use new and delete to allocate and construct variables of a single type, of a pointer type. We've noted that you can also pass in arguments to the constructor. You can use it with simple types as well as with complex user-defined objects. And anything you allocate using new, you clean up using delete. So anything you allocate plus construct using new, you clean up using delete. Let's look at an example of using new to instantiate a pointer type to a different object this time, different class, that is the complex number class. C dynamic is a pointer to the complex number class, and we call new complex number and in brackets pass in 10, 15. So we've dynamically allocated memory plus constructed an object using this new complex number, keyword, and statement. The 10, 15 basically is the arguments to the constructor. So if you remember, one of the constructors of complex number took in two doubles, a complex part and a real part. When we call new complex number and specify two arguments, C++ will automatically call the correct constructor. It will call the constructor with the corresponding number and type of arguments. Remember that a constructor is just a special function or a special method after all. So when it sees new followed by complex number and two arguments, it will call the corresponding two argument constructor of the complex number class. If you run the piece of code that you see on screen, you'll notice that the output looks something like this. So remember that we first dynamically assign the float that's from the last class. Check out the statement which says inside the two argument constructor. This basically indicates that when you run the code and this particular statement where you say new complex number and pass in two arguments goes inside the two arguments constructor and initializes the complex part and the real part of the complex number class. And then we have C dynamic arrow print. Remember to use the arrow operator, a hyphen followed by the greater than sign. Because C dynamic is a pointer, the way to access the member variables or the member functions within C dynamic is to use the arrow operator. The use of this arrow operator is what prints out to screen real is equal to 15 and complex is equal to 10, which is basically the setup, the internal member variables of the complex number class. Anything that we allocate and construct using new, for example, the C dynamic variable, which is of type complex number, we have to clean up using delete, which means that once we are done using C dynamic, we need to call the delete operation on it. A quick recap of what new and delete does. New first allocates the memory and then calls the constructor for your variable. That means the memory for complex number is first allocated and then the constructor is called. We also saw an example of this running code. Delete will first call the destructor and then deallocate memory for that variable. Let's see that in action. Going back to our complex number example and the code which allocates a pointer to a complex number by calling new. C dynamic is a pointer to a class of type complex number. It calls the two argument constructor, which we can see by running the code, and assigns the real part to 15 and the complex part to 10 for this complex number. Once we've used C dynamic, we now want to delete that variable. That variable should be cleaned up by calling the delete keyword. And if you notice the output, we can see that the destructor is called first. So when we call delete, the destructor is called. We can see the statement inside the destructor. Real part is equal to 15, complex part is 10. That's what we print out inside the destructor. So delete now calls the destructor and deallocates memory for this object. Let's now see an example of the next rule. using new with square brackets and delete with square brackets in order to deal with array variables. An array is a list of elements. The elements can be of simple types such as doubles, floats, etc., or it can be an array of classes or class objects. That's more accurate. So anytime you need to create an array of any type, we use new with square brackets, and this will not only allocate memory for the array but also construct the individual objects in the array. New in square brackets with square brackets will actually cycle through every element and call the constructor for every element in the array. Using new with square brackets only calls the default no argument constructor. You cannot call a constructor which takes in arguments by using the new keyword with square brackets. Once again, anything that you allocate using new with square brackets, you have to clean up using delete with square brackets. So these go together. New and delete, new with square brackets goes with delete with square brackets. The array new keyword or the new with square brackets allocates memory for the array and calls a constructor for every element in the array. It also knows how long the array is. It keeps track of the array length. Similarly, the delete with square brackets or the array delete keyword will first call the destructor for every array element and then deallocate the memory. Let's look at some code which uses the array new operator or the new with square brackets. Once again, we are going to use the complex number class and instantiate an array with 10 elements where each of those elements is a complex number. So C dynamic, a pointer to complex number, is basically an array which holds 10 elements of the complex number. Notice how we use the new keyword here. It's new complex number and in square brackets we specify 10. That's how we use the new with square brackets or the array new operator. Once we've used new to create 10 elements of the complex number type, we want to make sure that we can access each of those 10 elements. So we set up a for loop, iterate over the array, and print out that particular element in the array. What do we expect of each of these elements? We expect that the constructor has been called on each of these elements. The zero argument or the no argument constructor is the one that's been called, which means that the real part and imaginary part of each complex number element in this array is initialized to 0. See if you notice how we access each element in the array and how we access the methods on each element in the array. We use the dot operator and not the arrow operator to refer to an individual element of this array. Why is that? That's because the pointer is to the array itself. Each individual element in the array is a real object. It's not a pointer to an object. When we have a real object and not a pointer, we use the dot operator to access its member variables. If each individual element in the array had itself been a pointer, that's when we would use the arrow operator. We use the dot operator because each individual element in the array is an instance of the complex number class. It's not a pointer to an object of the complex number class. Notice that because we've used the new with square brackets or the array new operator, we use the array delete keyword, that is the delete with square brackets, to clean up this C dynamic pointer. If we use new with square brackets, we have to use delete with square brackets. They go together. What do you get when you run this bit of code? What's printed onto screen? Notice that we instantiate and allocate memory for 10 complex number objects. which means when we run this code, this is the output that we get. Remember that each time we construct an object of type complex number, we print this message to screen. The no argument constructor is called, indicating that the default constructor is what has been invoked. This is printed 10 times, indicating that for each of those 10 elements in the array, the default no argument constructor has been called. That's why this message is printed 10 times to our screen. All of this code should be available as a downloadable resource as a part of this lecture. You can go ahead and run it and see for yourself. Note that we've output exactly this message in the no argument default constructor. We've also initialized the real part and the complex part both to 0. So then we go ahead to the for loop, iterate over every element in this array, and print out the elements in the array. The output should be that every element in this array has its real part set to 0 and its complex part set to 0 as well. So we should be able to access every element in the array, and it should print out what we expect. Take a look at the code on screen and you'll realize that every element in this array has its real and complex part initialized to 0.0, which is obvious and the correct thing on the basis of the fact that the no argument default constructor was called. And finally, the array delete call of C dynamic. So when we call delete with square brackets on C dynamic, it goes ahead and calls the destructor on every instance or every object in that array. And if you run the code and look at the output, you'll notice that the destructor has been called 10 times, exactly what we would expect. We have this message inside the destructor which specifies that we are inside the destructor, and this message is printed out 10 times. This output is perfectly fine and exactly what we would expect. On to an example showing us what happens if rule number 4 is violated. If you remember rule number 4, it basically said that when you use new without the square brackets, then you have to use delete without the square brackets in order to clean up that variable. And similarly, when you use the array new with square brackets, you should use the array delete with square brackets to clean up that variable. So anything you allocate plus construct using new, you clean up using delete. And anything you allocate plus construct using array new, you clean up using array delete. If you mix and match these, basically your code will not work the way you expected. Do not mix and match these. The pairs are new and delete, array new, array delete with the square brackets. The best way to understand and internalize it is to take a look at what happens if you actually mix them up. Take a look at the example code. We've seen this before, where we have a pointer to complex number, which is an array. It's an array of 10 elements, and we allocate it by using the array new operator. That's the new followed by square brackets. So we've created an array of 10 objects. We know that the array new will allocate space for the array and call the constructor on each of the 10 elements. Notice how we free up the C dynamic, how we deallocate memory for this. We use the simple delete. We do not use the array delete. Notice the square brackets are missing. Now, what happens if you run this code? What happens? Now we've done a mix and match, which we said wasn't allowed. We've used the array new, the new with square brackets, but used the simple delete. So let's go ahead and run this code and see what happens. You can try this for yourself. You'll see an output which looks something like this. Error for object blah pointer being freed was not allowed. It basically just throws an error. You cannot compile and execute this bit of code. That's because the new using the array new does not match with the simple delete. You can't mix and match those. This is easily demonstrable. We've seen examples of how the rules work and what happens if the rules are violated. Let's take a look at another quirk, or you can say capability, that we can use with the new operator, and it's called the placement new operator. The placement new operator is essentially a variation of new. We've seen that new is used to allocate memory and construct an object. The placement new is a variation that ensures that an object resides at a specific memory location. By using the placement new, you can specify that this is the address where I want my object to live. Now, this isn't very commonly used in normal C++ programming, but if you're programming in embedded systems or in hardware components where space is limited, you might want to say that I want to allocate a object and it has to live exactly here because that's where the best access to other portions of the code is. You might have something like that. That's where you typically use the placement new operator. The placement new operator takes in the memory location as a parameter. So you specify the memory location where you want the object to exist, and this is a parameter to the placement new. The placement view new works a little bit differently from the new and the array new operators that we've seen so far. If you use the placement new, it's up to you to explicitly call the destructor on that object. Earlier, we could simply use the delete or the delete with square brackets, and that would take care of calling the destructor and deallocating the memory. In case you use the placement new, there is no corresponding placement delete. You'd have to explicitly call the destructor on the object that you allocated and constructed using placement new. Let's see how the placement new operator works with code. Take a look at the code on screen. It's a main method, and here we try to use the placement new operator. Don't worry, there's a lot going on here, but we'll be stepping through this code line by line and discussing what exactly each line does. Notice first how we allocate space. We set up a memory area where we want the object to live by using size of. Why does this work? We use a memory buffer, which is a character array. As you know, each character is typically 1 byte. Size of complex number will give us the size for that object in bytes. So we set up a memory buffer with the number of bytes equal to the size of complex number. That's what the very first line does. Memory buffer is a variable which holds enough space to store one complex number. Memory buffer holds the address, and we assign that address to place. That's a variable which is a void star. We set it up as a char star, but we don't really care that it's a char star. The reason we use character is to basically make sure that the number of bytes were equivalent, because a character is 1 byte. That's why we used a character array to set up the memory. Place is the variable which holds the address of the memory that we just allocated, and the size of that memory is equal to the size of complex number. Moving on to the next line. The next line assigns a pointer variable to a pointer of class complex number. The variable is called cPlacedNew, and see how it's allocated and constructed. We say new, that's the keyword, in brackets place, that's the address which the new keyword takes in as a parameter, and then what exactly we want to construct. That's the object of the complex number class. This calls the two argument constructor because the complex number class takes in two arguments for the complex part and the real part. The important thing to note here is that the new keyword takes in the memory location as a parameter. The memory location is specified by the void star place which we set up earlier in the previous two lines. Once we set it up, we use the C placed new exactly like we would any other pointer to a complex number. And then finally, if we use the placement new, you have to explicitly call the destructor. Note the line that's highlighted on screen. Note that statement. C placed new, arrow because it's a pointer, and tilde complex number. We've never explicitly called the destructor before. We've called the constructor using new, but we've never called the destructor. If you use placement new, it's your responsibility to call the destructor, which is what this line does. Are you confused yet? I won't be surprised if you are. The important thing to realize is that placement new isn't really that common. Don't use the placement new under normal circumstances. However, if you're writing embedded systems code or code that works with hardware applications, you're very, very close to the machine. That's when the placement new is useful. It's important for you to realize that the ability exists in C++. It isn't very commonly used, so don't worry so much about it. We've used a whole bunch of classes and instantiated objects so far. There is one implicit pointer within every object which you need to understand well so that you can use it. You'll find that it's very useful once you work further with classes, and that is the this pointer. This is highlighted because that's what the pointer is called. So let's do a brief recap. What is a class? The easiest way to define it for people who come from C is that a class is a struct, that's a logical unit, that contains functions in addition to data. Struct contains just data. A class contains functions which act on that data, and they form a logical unit. What is an object? This is also a good question and something you need to understand clearly. A variable of a class is called an object, or an instance of a class. The class itself is the template or the blueprint, whereas an object is an actual house or an actual instance which is formed from that template. So for one class, multiple objects can be instantiated from that one class. We've also studied during the course of this particular class that the data items inside a class are called member variables because they are members of that class. The functions within a class are called methods or member functions. That's because, again, these functions are members of the class and typically operate on the member variables. Every object that you instantiate from a class has its own copy of the member variables, and the member functions operate on those copies. My favorite way to imagine this relationship is to imagine the class as the blueprint for a house you're going to build. Each individual house you build using the same blueprint, and you can build multiple houses, is an object of that class. So the blueprint is the class, the object is the house itself. Every object has its own copies of the member variables. Every house you build from the blueprint has its own room. The room might look exactly as it's specified in the blueprint, but the room in one house is not the same as the room in another house, even though they've been both built from the same blueprint. The next thing we said was member functions of that object operate on those copies. Let's say there is a member function which says renovate this room. If you apply it to house 1 and you renovate one room in house 1, the same room in house 2 does not get renovated. That's why member functions operate on the own copies of the member variables. Now, these member functions can be arbitrarily complicated. Within the member function, how would you refer to the class itself? And that's where the this pointer comes in. Each object that you instantiate of a class has a special pointer called this, which points to that object itself. Note that it's each object, not each class. That means blueprint and house, each house has a special pointer called this, which points to that house. Within the house 1, it points to house 1, and within house 2, the this pointer points to house 2. I know the analogy is breaking down a little bit, but use this to imagine what the this pointer points to. The this pointer is used inside member functions of a class. The this pointer is used within a member function to refer to the object itself, as if the object were any other variable. You can always instantiate variables within a member function and refer to that variable by its name. But how would you refer to the object itself where the member function is running? You'd use the this pointer. It's an implicit pointer, and you can imagine that C++ injects it into every object of any class. The this pointer, you know whichever object you're in, whatever the class it instantiates, the this pointer always exists. So when is the this pointer valid? The this pointer comes into existence as soon as the object is created. So when we instantiate the object and call its constructor, the this pointer exists. And it continues to stay in existence till the object is destructed. So all the way up till the destructor, the this pointer can be used, which basically means anywhere in any member function of a class, the this pointer can be used. Let's take a look at the example on screen. Print this. Consider that this is a member function of the complex number class. The attached source code to these lectures should give you full details, but print this is the member function in the complex number class. Within the print this member function, notice the very first line. We say the address of this object is and output the this keyword to screen. The this keyword is actually a pointer that's implicitly set up by C++. It's valid in any class in any object. And this holds the address of this object. That means if you have an external variable that refers to this object, the address that that pointer variable holds is the same address as in the this pointer. The keyword this refers to the current object, which means if the current object is say C1, one complex number object, then this refers to C1. If the current object is C2, then this refers to C2. It refers to the current object. Note how we can access the member variables using this. This arrow real part prints the real part of the current object, whatever it is, C1 or C2. Similarly, this arrow complex part will print the complex part of the current object. It doesn't matter what that object is, this refers to the current object. Let's expand this example to understand a little bit better. We have the print this member function inside the complex number class. Let's say we have set up a pointer to the complex number class. We'll continue to use the cPlacedNew from the previous example. If you call cPlacedNew arrow print this, it will call the print this member function. Notice the second line where we print out the address at which C placed new is located, where the address of C placed new is. And also look at within print this where we print the address of the this pointer. C place new and this print out the exact same address, which means this points to the same address as an external variable that holds that object. It's confusing. You might want to spend a little time thinking about it. If you go ahead and run this code, you'll find that what we just mentioned was true. The address printed out within the complex number code, within the complex number class, by printing out this, and the address printed out when we print out C placed new is exactly the same. Take a look at the output and you'll see that this is true. The address of the this object is something, a very long hex number, and the address of our C placed new variable, the external variable, is exactly the same. The this pointer points to the current object and has the same address as an external variable which points to the same object. This brings us to the end of our section on new and delete. The this pointer is important to know and it's widely used. Often when you're referencing stuff within the current object, this is the most common way to refer to it. It may not be clear right now why this matters. Yes, we know this is a pun. However, later on, when we write more and more code in C++ using objects inheritance, we will need this, which is why we're learning about it right now.
If you've worked with strings in C at all, you know that they are a giant pain in the you-know-what. The theory of C strings makes them sound innocuous enough. They are arrays of characters terminated by a null character. The reality of using C strings, however, is that they make code extremely prone to errors. That's because the string in C is effectively a dynamically allocated class. It's a char star. And so all of the complexities of C dynamic memory allocation kick in. If you are not careful with using C strings, you will end up with memory leaks. To make matters worse, relatively simple and common operations such as copying, comparing, or moving strings require the use of the rather arcane C stir copy, stir CMP, and stir length kind of functions. All of that is changed in C++. Strings in C++ are just an absolute joy to work with when contrasted with strings in C. Almost invariably, you'll find yourself using the standard string class. This class, which is called string with lowercase s, exists in the std, i.e. the standard namespace. And this might be our first encounter with something really common and really powerful called a smart pointer class. The C++ string basically contains an underlying char star which holds the data, but it then does a whole bunch of clever stuff around it, reference counting and so on, and the result is that we have a string class which does basically everything that one needs. Sitting today in 2016, it's difficult to imagine the impact of the string class on the productivity of programmers in the late 80s and the early 90s when it was first added to the language. It was a huge improvement. And as with so many other parts of the C++ language, the C++ string class has set the benchmark for what string classes do in Java, C# and other more advanced languages. One little note though, C++ strings are different in their internal representation than C strings. So you cannot rely on a C++ string being delimited by the null character that we are so used to when working with C strings. But never fear, there are really easy ways to go from a C string to a C++ string and vice versa. We're going to cover all of these in the examples to come. In these examples, we will endeavor to try and cover all of the operations that we commonly perform on strings, creating, concatenating, manipulating, and comparing them. And we will find that all of these are very simple indeed in C++. And really, the incredible power of the C++ language is fully manifested in the string class. Smart pointers and operator overloading are both extensively used, and that's what makes all the difference. Before we plunge into the C++ string world, just a side note. You might recall that in C, the character data type is usually represented using a single byte. This is just enough to hold all of the ASCII values, which are the characters of the English alphabet. However, it's not enough to hold other alphabets from other languages such as Chinese, Japanese, Korean, or European or other languages. To get around this, the C++ character type has 2 bytes. The pre-existing character type char continues to exist, but the 2-byte character type is referred to as the wide car. That's the W car that you see on screen now. Just something to be aware of. This isn't something that we'll be using a lot of, but if you are working on localization, then this might be very relevant to you. In any event, let's move on and plunge into a bunch of string examples. Let's plunge into our first example. In this example, we are going to understand how to create, print, and concatenate C++ strings. Each of these operations is reasonably involved in C, but that's not the case in C++. Creating, printing, and concatenating strings in C++ is just incredibly simple. It's pretty much idiot proof. Let's go ahead and see how it works. Let's start by looking at a short snippet of code. I'll give you a second to glance over this code and just really quickly take in what it's trying to do. After that, we'll walk through it line by line. Before we plunge into the line by line, just check out the hash include, check out how we initialize or create a string, and check out how we concatenate 2 strings. Lastly, check out also how we print a string to screen. The first thing that catches our eye is the hash include that we need in order to work with strings. This is a typical C++ style include, and therefore we enclose the name of the header file in angle braces, angle brackets, and do not include the .h at the end. This is the way C++ headers ought to be included, as always. Remember again, the header is pretty obviously named and it's just called string. Next up, let's go and check out how string variables are initialized. The most common way, perhaps, of initializing a string is by passing in a string enclosed in double quotes. Both of these lines highlighted on screen now do just that. These effectively call the single argument constructor of the string class. This takes in a string and creates a string initialized with that value that was passed in. You should be aware that in addition to this one argument constructor, which takes in a string constant, the string class in C++ also allows you to initialize a string with a default value of a blank string, and you can also pass in a C-style car star. All of these will work while creating string objects. And next up is a line which ought to get you wildly excited if the only programming language that you know is C, but which you will be very blasé about if you already know Java or C#. And this is the way in which we concatenate strings in C++ simply using the plus sign. This again was huge when it was added to the C++ language. And this is also our first real encounter with an overloaded operator. What does that mean? The string class has overloaded the plus operator such that two string objects can be added together, and the outcome of that addition will be a third string. It's just so intuitive, it's very much like adding numbers. This operator overloading is a powerful and, in fact, a ubiquitously used part of the C++ language. We'll have an entire section on operator overloading and we'll go into all of the gory details. But for now, you should just be aware that operator overloading exists and it manifests itself in the form of string concatenations or string additions like those we see on screen now. And in fact, a measure of how powerful and how ubiquitous operator overloading is the fact that even in this really simple snippet of code, we have yet another example of operator overloading. The string class can be printed to screen using cout and the standard redirection operator that we use for all data types with cout. Now, this is only possible because of the operator put2 being overloaded. This put2 operator is what allows a data type to be written to cout. This operator is denoted using a couple of less than signs. This operator has been overloaded again so that a string object can be displayed to screen. Let's plunge into our first example. In this example, we are going to understand how to create, print, and concatenate C++ strings. Each of these operations is reasonably involved in C, but that's not the case in C++. Creating, printing, and concatenating strings in C++ is just incredibly simple. It's pretty much idiot proof. Let's go ahead and see how it works. Let's start by looking at a short snippet of code. I'll give you a second to glance over this code and just really quickly take in what it's trying to do. After that, we'll walk through it line by line. Before we plunge into the line by line, just check out the hash include, check out how we initialize or create a string, and check out how we concatenate two strings. Lastly, check out also how we print a string to screen. The first thing that catches our eye is the hash include that we need in order to work with strings. This is a typical C++ style include, and therefore we enclose the name of the header file in angle braces, angle brackets, and do not include the .h at the end. This is the way C++ headers ought to be included, as always. Remember again, the header is pretty obviously named and it's just called string. Next up, let's go and check out how string variables are initialized. The most common way, perhaps, of initializing a string is by passing in a string enclosed in double quotes. Both of these lines highlighted on screen now do just that. These effectively call the single argument constructor of the string class. This takes in a string and creates a string initialized with that value that was passed in. You should be aware that in addition to this one argument constructor, which takes in a string constant, The string class in C++ also allows you to initialize a string with a default value of a blank string, and you can also pass in a C style car star. All of these will work while creating string objects. And next up is a line which ought to get you wildly excited if the only programming language that you know is C, but which you will be very blasé about if you already know Java or C Sharp. And this is the way in which we concatenate strings in C++ simply using the plus sign. This again was huge when it was added to the C++ language. And this is also our first real encounter with an overloaded operator. What does that mean? The string class has overloaded the plus operator such that two string objects can be added together, and the outcome of that addition will be a third string. It's just so intuitive, it's very much like adding numbers. This operator overloading is a powerful and in fact a ubiquitously used part of the C++ language. We'll have an entire section on operator overloading and we'll go into all of the gory details. But for now, you should just be aware that operator overloading exists and it manifests itself in the form of string concatenations or string additions like those we see on screen now. And in fact, a measure of how powerful and how ubiquitous operator overloading is the fact that even in this really simple snippet of code, we have yet another example of operator overloading. The string class can be printed to screen using cout and the standard redirection operator that we use for all data types with cout. Now, this is only possible because of the operator put2 being overloaded. This put2 operator is what allows a data type to be written to cout. This operator is denoted using a couple of less than signs. This operator has been overloaded again so that a string object can be displayed to screen. Let's move on to our next example. This one centers around inputting strings from the user. Specifically, we are going to discuss how to input strings which include embedded blanks such as spaces or tabs, as well as embedded new lines, i.e. multi-line strings. There are some slight complications associated with inputting strings which have either embedded blanks or multi-line strings, and so let's make sure we understand them. As always, let's start with a simple snippet of code. Let's really quickly glance through this code and see what it does. It seems to be inputting a few strings and then inputting a compound string, asking the user for multiple lines, and then printing all of that stuff back out. In any case, let's dive in line by line. The first line that catches our eye is where we input a string from the standard input stream cin using the getFrom operator. This is exactly as we would expect for any other data type such as an int. This will read from the standard input stream, which is usually the keyboard input, take the string that it finds over there and assign it into the variable called first name. So to input a single string, just use cin. You should be aware, however, that cin is not going to work correctly for strings which contain either embedded blanks such as spaces or tabs, or for multi-line strings. What would happen if you tried to type in two words with a space in between? Only the first of those two words would be assigned to the first name variable. The second would just be lost. Likewise, there's no way for us to input a multi-line string because the cin stream will be flushed when the user hits enter. And this is where we've got to use a different function called getLine. GetLine is an overloaded function. That means that there are two different variants of this getLine function. The variant that we see on screen now is the one which we use to read in multiple lines. This particular variant takes in 3 arguments, the last of which is the delimiter, which indicates that the user has finished entering whatever he or she would like to type in. There is also a different variant of the getLine function, which we will get to in an example shortly, which is used to take in strings with embedded blanks, but which are not multi-line strings. In any case, more on that in a second. For now, let's focus on this particular variant of getLine and on its input arguments. The first input argument is the stream from where the string has to be read. In this case, this stream is simply Cin, which is the standard input stream. The second argument is the string variable into which the output from that stream is to be placed. This string variable here is something that we call user input. And the third argument is the character, which will signify that the end of the input has been reached. This is required because in a multi-line string, obviously, the default end of input character, which is just the enter or carriage return character, will not work. Here we specify a tilde. So again, what this function does in its entirety is take in a stream from where input is to be read, a string variable where that input has to be placed, and a character which indicates that the input has been terminated. Then takes all of this and stores it in that variable. This ought to be enough for us to fully comprehend the code that's on screen now. We prompt the user for the first and last name and then for the address being a multi-line string, and then we print all of this back out to screen. And here now is the output from when I just ran this program a second ago. The first portion asks me for my first and last names, which I type out. It then displays those back to screen, as you can see. And then it prompts me for my address. I go ahead and type my address on separate lines. And when I reach the end of my address, I type a tilde because that is the function, the character, that the getLine function was expecting. At the end, the program prints all of this back out to screen, and it's exactly as expected. So to recap, there are a couple of important points you should remember from this example. The first is that you can input string variables from Cin using the getFrom operator as usual. However, this will not work for strings which have multiple lines or have embedded spaces. In order to input such strings, there are two variants of the getLine function. Just make sure that you remember this and you'll do fine as far as inputting strings from the user goes. Let's move on to our next example, which involves carrying out a whole bunch of common string operations. I should add here that you should consider this example as representative, not exhaustive. This example will give you a flavor of the kinds of things that you can do with C++ strings, but you should be aware that there are a whole bunch of overloaded functions or similar functions which allow you to do an even richer set of operations with strings. So make sure that you read the docs. That said, none of them are rocket science. Once you've gone through this example, you'll have an excellent sense of how strings are to be manipulated. Okay, what's the first thing that we'd like to do with most strings? Having created a string, we'd like to know what the length of that string is. And there are two functions that allow us to do this. The first is the string size function. And note here, by the way, how the double colon, that is the scope resolution operator, signifies that this function is a member function of the string class. Using this function is pretty simple, and here's a simple example on screen now. If you have a string variable, you can tell how many characters it has by using the fullName.size method. Note here that this does not tell us the number of bytes that this string object occupies. That's something that you would use the sizeOf function for. Again, remember the size method. Size is a member function of the class string, as we can see from the scope resolution operator with the two colons. This member function returns the number of characters of a string. It turns out that there is yet another way to perform the same calculation, and that is by using the very similarly named length function. This behaves in exactly the same way. Again, this is a member function of the string class, and this again will return the number of characters just like size. And here on screen is an example of calling or invoking the length member function on an object of class string. Next up, let's go ahead and figure out how to calculate the substring of a string. Again, there is a really handy member function which is called subster. That's what you see on screen now. Let's figure out how this is used. And there is the usage. This line of code enables us to find the substring of this string variable, which includes the first 3 characters starting from position 0. And those are exactly the 2 numbers that we've got to pass into the function. The first function parameter is the starting index of the substring, which here is 0. Remember that the indices of strings, like of arrays, start from 0. So the starting index is 0. The next function parameter is the length of the substring in characters. Here we are specifying that we would like a substring of length 3 characters. Next up, let's talk about how we would modify strings, starting with the erase operation. And there again, we have a pretty obviously named member function called erase, which is used exactly like the subster function. Again, the function arguments that this method takes in are the starting index of the substring, which here we specify to be 0, and the number of characters to be erased, which here again we specify to be 3. In other words, erasing a substring is not that difficult from finding a substring of a string and setting each of those corresponding values in the string to nothing. This will reduce the length of the string. To increase the length of the string, we use the insert member function. And this again is a member function as evidenced by the use of the scope resolution operator. And again, it takes in a few obvious parameters, namely the position in the original string where we are to insert. That's the first function argument, which here is specified to be 0. And then the second is the substring that has to be inserted. This could be another string variable, and that's what it is in this instance. Effectively, what we've done in the operations which we've gone through is we first found a specific substring of a string. We then erased that substring from the string, and now we are reinserting it using the insert function. Okay, let's now move on to searching inside strings. Now there are loads and loads of different member functions which allow us to search inside strings. The most common is the find function. Here we search for the position of some string inside another string, and the return from this function is the position, which is an index, i.e. the starting point starting from 0. You should remember that in C++, an unsigned int variable has an alias, and that alias is size underscore t. Now don't ask me exactly why this alias exists, but it's pretty common. And I guess it's a reasonably intuitive way of making clear that the return value from this function is a position. Okay, moving on to the other arguments or the other parts of this line. The input argument is what string is to be found. Here again, this is a string variable, i.e. we are searching for one string inside another. The next obvious question is, well, what string are we searching inside? And this is the full name string. In other words, full name is the string which is receiving this function call. It's the receiver. And the output of this function is the position, the starting index of that string if it was found. And if not, it's a special value called npos. Now this brings us face to face with a string specific constant. This is a const static member of the string class, which we'll talk about later. But for now, just remember that this is effectively like a hash define. This is a special value. We should always check for this special value when we search for one string inside another. This is yet another example of how C++ is just so much tighter and safer than C. In C, all we'd have done in an operation like this is check whether the returned value was less than 0. Even if we did compare it against a constant, that constant would have been a global constant defined using the hash define preprocessor directive. Here in C++, the constant has a specific meaning, and that meaning is tied to the class that contains it. We'll have more to say on const static members later on, but just remember that in C++, you should define constants in this way rather than by using hash defines. Let's now go through and put to use all of the functions that we just saw. Before we do that, I'd like to remind you that we've only discussed a reasonably small but representative fraction of the functionality available for working with strings. There are lots of functions that we have not discussed which are variants of these. As an example, we discussed the find function, but we did not discuss its close relatives, which include find first of, find first not of, rfind, which will search from the end of a string, and rfind last of. There are a whole bunch of these functions which do pretty much exactly what their names would suggest. So once you know how to use the find function, you should be able to use all of these other functions as well. You can always Google for specific functions if you have something specific that you need to do and are flummoxed on. Okay, let's now really quickly run through and make use of all of the functions that we just discussed. On screen now, you can see a snippet of code which prompts a user for his first name, last name, and nickname. It then concatenates the first name and the last name and stores this value in a variable called the full name. Next up, it prints the number of characters in the full name in two different ways, using both the name fullname.size method and the fullname.length method. We already discussed that these are synonymous. Both of these will return the number of characters in a string. Just to be clear, they will not return the number of bytes occupied by the string object. And we print the output to screen, and you can see that indeed the number of characters is returned correctly to be 17. That's the number of characters in my full name, not including any blanks. Moving along, let's find a substring of my first name. And this is a substring that starts at index 0 and is of length 3. Having done that, let's then go and print out to screen what we found. And you can see again, because we are doing all of this with my name, the substring that includes the first 3 characters starting from 0 is bit, that's VIT, and that indeed is what is printed to screen. The substring method finds a substring and returns it as a separate string variable. Let's do something a little more destructive. Let's go ahead and erase a part of a string using the erase function which we just discussed. This member function of the string class doesn't return anything because it's operating on the receiver, i.e. on the first name string object. We specify that we would like to erase 3 characters starting from index 0. What that leaves is the last 4 characters of my name, THEL. Now that of course doesn't make a whole lot of sense. It's not even a real name. So let's go ahead and reinsert the substring which we just deleted at the start of the first name. Having done this, we will get my original name back. Why did this happen? Well, remember that we used the substring function to get the first 3 characters of my name. We then use the erase function to delete the first 3 characters of my name. And we then use the insert function to reinsert those first 3 characters into the start, and that left us back with my original full first name. Okay, let's now go ahead and check out how we do a search and replace inside a string. Here we are going to prompt the user for a nickname and then replace the first name with that nickname. That's the code that you see on screen now. Let's walk through it line by line so we understand how it worked. It all begins by prompting the user for the nickname. Here I was prompted for my nickname and I typed it in as Humpty Dumpty. Now I'm not going to actually reveal whether this is my real nickname or not, but for the purposes of this example, let's assume that it is. I went ahead and typed in Humpty Dumpty in response to the question on screen, and then the program displayed this back using the cout operator. So far, nothing very profound going on. Next up, since we want to replace the first name with the nickname, we've got to find the position of the first name inside the full name. We do this using the find method on the full name object. Remember that the full name was merely the concatenation of my first name and my last name. In other words, the first part, the first substring of the full name was just going to be my first name. And that's what we want to replace with the nickname. This now gets us to the most interesting part of this little search and replace operation. There are a whole bunch of ways in which I could have accomplished this. The way I'm going to do it is by first replacing every character from my first name with a blank character. This has the same effect as calling erase on the full name, and then reinserting the nickname into that position. Okay, let's break that down. We first replace everything starting at the position of the first name, which we just found, with the empty string. We do this for how many characters? For the number of characters which are in the first name, i.e. for the first name dot length. The result would be to change the contents of the full name variable from Vittal Srinivasan to just Srinivasan. Why? Because all of the characters in Vittal have been replaced with the empty string. Now, having accomplished the first part of this operation, let's get to the second. And here we reinsert the nickname into the full name at the position of the first name. That position is simply 0. And doing this will leave us with the full name string variable containing Humpty Dumpty Srinivasan, which is what we had in mind. Why? Because my nickname was Humpty Dumpty, my first name was Vittal, and the operation was to search and replace my first name with my nickname. And this is exactly what's printed to screen now. Let's move on to our next example, which involves carrying out a whole bunch of common string operations. I should add here that you should consider this example as representative, not exhaustive. This example will give you a flavor of the kinds of things that you can do with C++ strings, but you should be aware that there are a whole bunch of overloaded functions or similar functions which allow you to do an even richer set of operations with strings. So make sure that you read the docs. That said, none of them are rocket science. Once you've gone through this example, you'll have an excellent sense of how strings are to be manipulated. Okay, what's the first thing that we'd like to do with most strings? Having created a string, we'd like to know what the length of that string is. And there are two functions that allow us to do this. The first is the string size function. And note here, by the way, how the double colon, that is the scope resolution operator, signifies that this function is a member function of the string class. Using this function is pretty simple, and here's a simple example on screen now. If you have a string variable, you can tell how many characters it has by using the full name.size method. Note here that this does not tell us the number of bytes that this string object occupies. That's something that you would use the size of function for. Again, remember the size method. Size is a member function of the class string, as we can see from the scope resolution operator with the two colons. This member function returns the number of characters of a string. It turns out that there is yet another way to perform the same calculation, and that is by using the very similarly named length function. This behaves in exactly the same way. Again, this is a member function of the string class, and this again will return the number of characters just like size. And here on screen is an example of calling or invoking the length member function on an object of class string. Next up, let's go ahead and figure out how to calculate the substring of a string. Again, there is a really handy member function which is called subster. That's what you see on screen now. Let's figure out how this is used. And there is the usage. This line of code enables us to find the substring of this string variable, which includes the first 3 characters starting from position 0. And those are exactly the 2 numbers that we've got to pass into the function. The first function parameter is the starting index of the substring, which here is 0. Remember that the indices of strings, like of arrays, start from 0. So the starting index is 0. The next function parameter is the length of the substring in characters. Here we are specifying that we would like a substring of length 3 characters. Next up, let's talk about how we would modify strings, starting with the erase operation. And there again, we have a pretty obviously named member function called erase, which is used exactly like the subster function. Again, the function arguments that this method takes in are the starting index of the substring, which here we specify to be 0, and the number of characters to be erased, which here again we specify to be 3. In other words, erasing a substring is not that difficult from finding a substring of a string and setting each of those corresponding values in the string to nothing. This will reduce the length of the string. To increase the length of the string, we use the insert member function. And this again is a member function as evidenced by the use of the scope resolution operator. And again, it takes in a few obvious parameters, namely the position in the original string where we are to insert. That's the first function argument, which here is specified to be 0. And then the second is the substring that has to be inserted. This could be another string variable, and that's what it is in this instance. Effectively, what we've done in the operations which we've gone through is we first found the specific substring of a string. We then erased that substring from the string, and now we are reinserting it using the insert function. Okay, let's now move on to searching inside strings. Now there are loads and loads of different member functions which allow us to search inside strings. The most common is the find function. Here we search for the position of some string inside another string, and the return from this function is the position, which is an index, i.e. the starting point starting from 0. You should remember that in C++, an unsigned int variable has an alias, and that alias is size underscore t. Now don't ask me exactly why this alias exists, but it's pretty common. And I guess it's a reasonably intuitive way of making clear that the return value from this function is a position. Okay, moving on to the other arguments or the other parts of this line. The input argument is what string is to be found. Here again, this is a string variable, i.e. we are searching for one string inside another. The next obvious question is, well, what string are we searching inside? And this is the full name string. In other words, full name is the string which is receiving this function call. It's the receiver. And the output of this function is the position, the starting index of that string if it was found. And if not, it's a special value called npos. Now, this brings us face to face with a string specific constant. This is a const static member of the string class, which we'll talk about later. But for now, just remember that this is effectively like a hash define. This is a special value. We should always check for this special value when we search for one string inside another. This is yet another example of how C++ is just so much tighter and safer than C. In C, all we'd have done in an operation like this is check whether the returned value was less than 0. Even if we did compare it against a constant, that constant would have been a global constant defined using the hash define preprocessor directive. Here in C++, the constant has a specific meaning, and that meaning is tied to the class that contains it. We'll have more to say on const static members later on, but just remember that in C++, you should define constants in this way rather than by using hash defines. Let's now go through and put to use all of the functions that we just saw. Before we do that, I'd like to remind you that we've only discussed a reasonably small but representative fraction of the functionality available for working with strings. There are lots of functions that we have not discussed which are variants of these. As an example, we discussed the find function, but we did not discuss its close relatives, which include find first of, find first not of, rfind, which will search from the end of a string, and rfind last of. There are a whole bunch of these functions which do pretty much exactly what their names would suggest. So once you know how to use the find function, you should be able to use all of these other functions as well. You can always Google for specific functions if you have something specific that you need to do and are flummoxed on. Okay, let's now really quickly run through and make use of all of the functions that we just discussed. On screen now, you can see a snippet of code which prompts a user for his first name, last name, and nickname. It then concatenates the first name and the last name and stores this value in a variable called the full name. Next up, it prints the number of characters in the full name in two different ways, using both the name fullname.size method and the fullname.length method. We already discussed that these are synonymous. Both of these will return the number of characters in a string. Just to be clear, they will not return the number of bytes occupied by the string object. And we print the output to screen, and you can see that indeed the number of characters is returned correctly to be 17. That's the number of characters in my full name, not including any blanks. Moving along, let's find a substring of my first name. And this is a substring that starts at index 0 and is of length 3. Having done that, let's then go and print out to screen what we found. And you can see again, because we are doing all of this with my name, the substring that includes the first 3 characters starting from 0 is a bit, that's VIT, and that indeed is what is printed to screen. The substring method finds a substring and returns it as a separate string variable. Let's do something a little more destructive. Let's go ahead and erase a part of a string using the erase function which we just discussed. This member function of the string class doesn't return anything because it's operating on the receiver, i.e. on the first name string object. We specify that we would like to erase 3 characters starting from index 0. What that leaves is the last 4 characters of my name, THEL. Now that of course doesn't make a whole lot of sense. It's not even a real name. So let's go ahead and reinsert the substring which we just deleted at the start of the first name. Having done this, we will get my original name back. Why did this happen? Well, remember that we used the substring function to get the first three characters of my name. We then use the erase function to delete the first three characters of my name. And we then use the insert function to reinsert those first three characters into the start. And that left us back with my original full first name. Okay, let's now go ahead and check out how we do a search and replace inside a string. Here, we are going to prompt the user for a nickname and then replace the first name with that nickname. That's the code that you see on screen now. Let's walk through it line by line so we understand how it worked. It all begins by prompting the user for the nickname. Here, I was prompted for my nickname and I typed it in as Humpty Dumpty. Now, I'm not going to actually reveal whether this is my real nickname or not, but for the purposes of this example, let's assume that it is. I went ahead and typed in Humpty Dumpty in response to the question on screen, and then the program displayed this back using the cout operator. So far, nothing very profound going on. Next up, since we want to replace the first name with the nickname, we've got to find the position of the first name inside the full name. We do this using the find method on the full name object. Remember that the full name was merely the concatenation of my first name and my last name. In other words, the first part, the first substring of the full name was just going to be my first name. And that's what we want to replace with the nickname. This now gets us to the most interesting part of this little search and replace operation. There are a whole bunch of ways in which I could have accomplished this. The way I'm going to do it is by first replacing every character from my first name with a blank character. This has the same effect as calling erase on the full name, and then reinserting the nickname into that position. Okay, let's break that down. We first replace everything starting at the position of the first name, which we just found, with the empty string. We do this for how many characters? For the number of characters which are in the first name, i.e. for the first name dot length. The result would be to change the contents of the full name variable from Vittal Srinivasan to just Srinivasan. Why? Because all of the characters in Vittal have been replaced with the empty string. Now, having accomplished the first part of this operation, let's get to the second. And here we reinsert the nickname into the full name at the position of the first name. That position is simply 0. And doing this will leave us with the full name string variable containing Humpty Dumpty Srinivasan, which is what we had in mind. Why? Because my nickname was Humpty Dumpty, my first name was Vittal, and the operation was to search and replace my first name with my nickname. And this is exactly what's printed to screen now.